Okay. So chapter rules, pi. So if we want exact radians, we have to undo the degrees. So you have 838 in degrees. So the conversions are pi radians is the same as 180 degrees. If you want to undo degrees, you got to divide by degrees, and you need radians in the numerator because you want radians over here. So there are pi radians in 180 degrees. That way your degrees over degrees reduce, and all you have left are radians. You have in the middle 838 over 180 pi radians. But you have to simplify it to lowest terms. So we want a fraction. Well, let's see. That's not divisible by 3. I'm just going to go with 2. 838 divided. You can use calculator, but I'm not going to run over there. 2, 4, and we get a 1, and this is a 2, so it goes in 412 times. That's not 12. Yeah. Come on, exactly. So, whoops. This is 2 times 419. This is 2 times 90. So 419 over 90 pi. And how do you know that you're done? Well, the only thing going into 90 is a 2 times a 45, or a 3 times a 30, or 4 doesn't work, 5 times an 18, 6 times a 15, 7 doesn't work, 8 doesn't work, 9 times 20, and 10 times 9. No, yeah, 10 times 9 times 20, 10 times 9, 9 times 10. And 419 is not divisible by any of those. So 419 pi over 90 radians. If you don't put radians on, okay. But why not? Because that's what you do. Good question. And I will ask you to change degrees into radians. I'm not going to ask you, oh, here's the switcheroo. I'm going to give you radians. You make degrees out of it. That will be on your test. You're going to do one this way. You do one going the other way. All right. But for the quiz, it's going to be just like this. Okay. The exact length of the arc on a circle. Radius intersected by a central angle theta, we the answer in terms of pi. Well, only if you have pi. I ain't got no pi. I have a radius of 0.5 meters, and theta equals 15 what? You see a degree symbol? No. So it's not degrees. It's exactly 15 radians. How do you know whether it's degrees or radians? If it's degrees, there's a degree symbol. If you don't have a degree symbol, that means it's exactly 15 radians. So that means the radius wrapped around that arc 15 times around the circle. Okay, like 1 times the radius going around the circle would be 57 point something degrees. That's what we're talking about. You can have exact integer values without pi's. It doesn't have to have a pi if you have radians. You can have a 1 radian, a 2 radian, a 3 radian. 3 radians, if you had a 3 radian, would that terminate in quadrant 1, 2, 3, or 4? If it was exactly 3 radians. An angle of 3 radians. Would it terminate in quadrant 1, 2, 3, or 4? Which one? Quadrant 2. Because is it exactly 180 exactly pi? That's exactly pi, which is 3.14159, keep on going. So this is more than 3. So if this is more than 3 here, then 3 radians would be just short of it. Right here is where 3 radians is in quadrant 2. Okay. Exactly 6 radians, exactly the number 6 would be in quadrant 4 because all the way around is 2 pi. 2 pi is approximately 6.28 radians. So if you have exactly 6, then you're going to be just short of 2 pi. So 6 radians would be right up there. So if you're looking at 15, well, you just keep on going. Okay. And so 3 times pi, that's 3 times almost 3.14. So that's more than 9. 4 times pi, 4 times 3.14, that's more than 12. 5 times pi, 5 times 3.14, that's more than 15. 5 pi. Not that you have to do this, I'm just giving you that you can have 15 exact radians. 5 pi, so there's 1 pi, 2 pi, 3 pi, 4 pi, here's 5 pi. So 15 radians would be just short of right there. It would be around here, around here again, and then right here. 15 radians. So what distance did a point around that circle travel? Because this is radians, S equals r theta. So S is just equal to 0.5 times 15. So S is equal to 7.5, and then over to meters. Now, directions. Write final solution in the given space where provided. So at the bottom of this box, because you're actually solving for something, what does S equal? There will be S equals what? Make sure you put your final answer where I can find it nice and neatly. 7.5 meters. It's like if you were doing a Scantron test and you didn't bubble it in on the Scantron sheet, you just circled it on your test, but you bubble it in, you get it wrong because I'm shoving them through a Scantron machine and it's not going to read what you wrote on the test. It's going to read what you didn't bubble in. Okay. So make sure you put it there. If there is one, like this one, didn't have one, you just write your answer. And then I got a bonus question. This one is calculator generated. Round your answer to the nearest hundredth because these guys are given in decimal. This one you are given degrees. Find the radius. Find the radius. Now, if you want to use the radian formula, you have to convert this into radians. If you want to use S equals r theta, you got to convert the degrees into radians. But you have an equation that has arc length in degrees. if you have degrees, the arc length is equal to theta in degrees at a 360 degrees times 2 pi times the radius. Remember, it's just a fraction of the whole circumference. So we know that S 8.465 is equal to 265 degrees out of 360 degrees. The degrees are going to reduce. Times 2 times pi times the radius. So 8.465 is equal to, now, since you get to have decimals, you can convert all of this into decimals. I'm just going to go 265 and divide by 360. And then that decimal times 2 pi times 2 times pi. Don't just plug in 3.14 for pi. You have a calculator that has the actual pi button. So it would use all of basically the entire digits of pi as it calculates it, because you don't want to round until the end. That way you have the most accurate of answers. So what this decimal is right here is 4.625122518 times the radius. And then you divide both sides by 4.625122518. And we get the radius is equal to. So I don't have to retype that number in my calculator. I'm going to punch in 8.465 divided by the last answer that was in my calculator, which is 4.625122518. I'm going to type that in by just doing right here above the negative symbol is ANS, which stands for answer. It's going to punch in right underneath that fraction. It's going to punch in the last answer that came out of my calculations. So to activate the ANS, which is in blue, you got to hit the second button. So second. And then that negative symbol. And it's going to take the 8.465 and divide by the last answer in the calculator. And we get a radius of 1.8302211787. Then round to the nearest hundredth. The hundredth is 2 decimal places. So that would be the 3, the 0 keeps us a 3, so 1.83 units. Yards. The radius is a length, and the arc length was given in yards, so that's our unit because it would be a length as well, yards. That's the bonus question. Okay, ask today's quiz. Open note. Do you have any questions from 5.1's homework that you want to see before we actually do the quiz that we haven't covered? Oh, I feel like one of those machines that's got to grab, some toy. Oh, yeah, it's a claw. I'm not pretty sure. I'm not sure if I'm actually big enough or not. If I don't think enough, I think I'll put another cord. Okay. Is there anything from the homework 5.1? One, two. Yeah, post this thing. Blue radius is approximately 12 centimeters in diameter. The drive motor of the Blu-ray player is able to rotate 10,000 RPM, depending on what track is being read. Because I am so visual, as soon as I start to read things, I need to start to write things down. It's like having the pieces of the puzzle out on the table in front of me so I know what I have to work with. We have a Blu-ray disc, 12 centimeters in diameter. So the diameter is 12 centimeters. So we're looking at a Blu-ray disc, and all the way here is 12 centimeters, which means the radius would be 6. Just in case, that might save some time, don't know. But what else do I have? 6 centimeters like that. All right. Revolutions per minute. Spins at approximately 10,000 RPM. Depending on what we're trying to do. Find the maximum angular speed, and here's the hint. They're telling us what units they want in radians per second. So we're going to have to convert. All we know is that it goes at 10,000 revolutions every 1 minute. And we got to convert that into radians every second. And that's because they phrased the question that way, and that's exactly how I'm going to phrase it. I don't think that it's not fair to just tell you convert it into an angular speed and not tell you whether or not I want degrees or radians and not tell you what unit of time I want you to give me. Okay. We want radians instead of revolutions, and we want seconds instead of minutes. And honestly, don't try to like undo each one all at once. Just take care of either the time first, or take care of the revolutions first. Convert the revolutions into radians, or convert minutes into seconds. It's up to you. Time or revolutions, which one do you want to undo? Time. So we want seconds down here. So if we want seconds down below, then we're going to have to multiply by minutes. So what's the conversion, minutes and seconds? There's how many whats and whats? So there's 60 seconds for 1 minute. And now you can see that your minutes will reduce. And all you have are seconds down below. So now we got to get rid of revolutions and convert it to radians. So if you have that disc spinning and it makes 1 revolution, how many radians is in 1 revolution? 2 pi radians in every 1 revolution. So that's gonna be your conversion number. I want radians in the numerator. So I'm gonna want radians up here. And I want to undo revolutions, so I need revolutions down here. So that means to undo revolutions, for every one revolution, there are 2 pi radians. And now you can see that revolutions divided by revolutions reduce. So on the left-hand side, the only unit you have are seconds. And the numerator, all you have are radians in the numerator. You have 10,000 times 1 times 2 pi. Down below, you have 60. So I see you can divide by 10. That takes care of that 0. 2 goes into 6. 3 times. Useless. Goes into 6 3 times. So that's 1,000 times a pi left over 3 radians every second. I don't know if they want decimal or not. I would have to look at the back of the book and check the answers. But that would be the exact value. Let me see. It doesn't say. On your test, I won't tell you the exact value. Okay. And it says find the maximum speed, the linear speed. So now we want distance. Linear speed would be distance divided by time. And they give us the unit in meters per second of a point on the outermost track as the disk rotates. So how fast is a point out here moving along the disk as it rotates? And for part B, again, they give us a hint. The final answer, meters per second. And all you know is in every, 10,000 revolutions per minute. You know how to get rid of minutes and change them to seconds. So let's do that again. So to get rid of minutes and change it to seconds, for every 1 minute on the top, you need 60 seconds down below. So that's going to undo the minutes. And now you have revolutions every second. But now we need meters per second. Every one revolution, the arc length is the circumference. Every one revolution, the arc length is basically 2 times pi times the radius. But, what's 2 times the radius? If you went 2r pi, you get just pi, pi times d, or d times pi. The diameter times pi. So they gave us 12. So technically 12 pi, or 2 times 6 times pi. But the problem is that's centimeters. So you have 1,000 or 10,000 revolutions every 60 seconds. And in every one revolution, it's going 12 pi centimeters around. So now we've got to change centimeters into meters. So what's the conversion centimeters to meters? There's how many what's and what's? There's 100 cents. Century is 100 years. A cent is 1/100th of a dollar. A centimeter is 1/100th of a meter. So 1/100th of a meter means you have 100 centimeters in a meter. I want to get rid of centimeters, and I want meters on the top. So I need to divide by the centimeters, and there's 100 of those for every 1 meter. So now when you look at the revolution reduces, the centimeters reduce. So we have 10,000 times 12 pi. That's a 1, and get the meters over 60 times 100. And there's your second, so you have your meters per second. And 2 zeros is going to reduce 2 zeros right there, 100. So you're left with 10,000 divided by 100 is now just 100. Wow, there's 2 green stuff. 100 left over. And then you got a 10 goes into 100. So you're just left with now a 10. So 10 times 12 pi over a 6. That 6 goes into the 12 2 times. So you're left with a, that's gone. So 10 times 2 times pi, that's 20 pi meters every 1 second, or meters per second. So do they have decimal in the back? Did you look? So 20 times pi is going to be basically about 60 something. Yeah. But it's just about the units doing their thing. I don't like memorizing formulas. I don't. The units you just need to think through your units. Take care of time. What kind of time do you want? I want seconds. Where do you want it? In the denominator. So you got to undo the denominators. Get it to where you need it. That way you don't multiply by the wrong thing. Some people might, and fortunately, right here, put 60 seconds on the top, 1 minute on the bottom. That's not going to undo it. Now you got minutes squared at the bottom, 60 seconds on the top. Any others in 5? I clean things up, and then where I put things away, This, oh, we can do this. Right. Fundamental trig identities. So we went over SOHCAHTOA for right triangles. We talked about the reciprocal identity, the reciprocal trig ratios for SOHCAHTOA. So if you flip over sine, flip over cosine, flip over tangent, we have reciprocal identities. We have cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Now, they are reciprocals of each other. I'm not just going to try to copy the board. I am just trying to do is write it over on the side so we have reference to it. We need these because, as they say, fundamental identities. Trig, its major purpose, especially when you move on to the next level, which is calculus. There are so many problems in calculus that we cannot do algebraic, just cannot be done. So you have to convert it into a trig equation. If you're able to convert the algebra into trig, then we can do it. And it's trig identities that allow you to do it. It's basically playing this game. It's an alter ego for these trig identities. It's an identity. It's like Batman has a secret identity, Bruce Wayne. Okay, or Damian Wayne, depending upon what Batman you're reading. Bruce Wayne is his secret identity. He has another identity. Sine, cosine, tangent, they all have other identities. Sine can be written as the reciprocal of cosecant theta. Likewise, cosecant theta is the reciprocal of sine theta. I can replace cosecant theta with 1 over sine theta. I can replace sine theta with 1 over cosecant theta, and vice versa. Equals works in both directions. I can replace this with that, or I can replace this with this. It just depends upon what do I need to do? What am I trying to simplify? What am I trying to make? What would make my life easier? And it's these substitutions that we need to know. These are the fundamental ones, and we're going to use them so often, it's going to be that's basically etch a sketch right into your head. Just don't shake your head. Okay. Cosine and secant go together. Cosine theta is the reciprocal of secant theta. Likewise, secant theta is the reciprocal of cosine theta. And tangent goes with cotangent, obviously. And theta is 1 over the cotangent of theta. And cotangent theta is the reciprocal of tangent theta. They are reciprocals of each other. Now, we'll see that you can also write tangent as a ratio of sine and cosine. Now, that's not going to be relatively proven to you yet, but it really will come into play when we start working more with the unit circle. But tangent theta has a couple of extra identities. In March, Marvel, Disney Plus, the Marvel series things that they've been doing with Hawkeye and Winter Soldier and Falcon and Scarlet Witch, Vision, WandaVision. Another one starting up in March, Moon Knight. Moon Knight is Marvel's version of Batman. except Moon Knight's better. Because Batman's overrated. I'm sorry. He's just way overrated. And everybody's a Batman fan. Ooh, Batman. Anyway. Moon Knight has a problem. He has multiple personality disorder. He doesn't really know who he is. And that's basically, he is completely whacked. He doesn't know who he is, when he is, and what triggers. Multiple identities. Tangent can be written as the ratio of sine theta divided by the cosine theta. And since cotangent is the reciprocal, cotangent would be cosine theta over sine theta. Okay. This one right here, these three are the next three. I'll tell you right now. Yeah, I know all three. I know of them. But I only know one by heart. The most important one gives you all three to begin with. The most important one is going to give you so many more. This first one right here, I like to call BDT, the Big Daddy theorem. This one drives everything home. If you know the first one, you know everything. That first one gives you so much. Sine squared theta plus cosine squared theta is always equal to 1. This one I am going to prove. Big Daddy theorem. This is also known as the Pythagorean identity. The sine squared of theta plus the cosine squared of theta is always equal to 1. So here's my right triangle. And I actually drew part of it over there. So this is angle P, this is angle R, this is angle Q. Now, this is how you label a triangle when you do geometry or trig. The vertices of the triangle are capital letters, uppercase. The opposite sides are labeled with lowercase letters. So if this is capital P, this is lowercase p. If that's uppercase Q, this is lowercase q. And if this is capital R, uppercase R, then the hypotenuse across from it is going to be lowercase r. Okay? So this is for any triangle. I'm going to label this my angle theta right here. So the sine squared of that angle theta plus the cosine squared of this angle theta adds up to 1. Always. So let's see. First of all, the sine of that angle theta is equal to opposite over hypotenuse. So that's P over R. And the cosine of that angle theta is equal to adjacent over hypotenuse. So that's equal to Q over R. Okay? Stay. Anyway. According to the Pythagorean theorem, the leg of a right triangle squared plus the other leg of a right triangle squared is equal to the hypotenuse squared. Or in this case, okay, q squared plus p squared is equal to r squared. Okay? Now, we just got done saying that the sine of theta was equal to p. So what does p equal? 9. Wow. Is that over your head? No, it's not like that. What does p equal? How do I solve for p? Yep. Multiply both sides by r. It's being divided by r, so you multiply by r. So r times the sine of theta. P equals r sine theta. Hello, substitution. R sine theta, and we're going to square it. That's P. What does Q equal? Multiply both sides by r. So Q is equal to r times the cosine of theta. So r times the cosine of theta squared. And that is still equal to r squared on the right side. Okay. When you square a product, you just square, or when you raise any product to a power, you can raise the individual factors to a power. So r times cosine theta to the second means we have r squared times cosine squared theta plus r sine theta squared is r squared times sine squared theta equals r squared. Now, I'm going to explain something to you and why it's important. Do you notice for sine, cosine squared, cosine squared, where the square is? Okay. This square, because technically sine theta, if you write sine theta and you just do this, the way you just wrote that means you're squaring the theta, not the sine. So in other words, you're taking the sine and you're supposed to square the angle first and then take the sine. So if you actually want to take the square of sine theta, you would have to every time put it in parentheses. You take the sine of theta first and then you square the whole thing. Now, you know how lazy students are. They don't put parentheses when they're supposed to. So somebody in the past, I don't know who, they decided, all right, when you mean this, you can just put sine squared theta. So you're going to take the sine of theta and then you square it. So that's why the square is on the end if you're squaring the sine after you do the sine of theta. Okay? Pleasure. All right. Remember there's something called, it's an F word. 6 letters, factor. On the left-hand side, r squared cosine theta, r squared sine theta, they have a common factor of r squared. So I can factor r squared out of each one. So r squared times, when you factor out, you're dividing each one by r squared. So when you factor out the r squared, I just have cosine squared theta plus sine squared theta equals r squared theta. I'm sorry, r squared. Reconnect, it sounds like, you know, trying to meet up with people that left me a long time ago. And then r R squared times means I can divide both sides by R squared. So I will all see the reason why this is important. It doesn't matter how big the angle theta is. Doesn't matter how big angle theta is, no matter what, because I'm doing it with variables, you will always get cosine squared theta plus sine squared theta equal to 1. One of the most important identities you will ever come across. Sine squared plus cosine squared equals 1. Cosine squared plus sine squared, doesn't matter, equals 1. Because it's going to allow you to make a lot of substitutions. And again, not just necessarily in trig, but they come in handy in calculus. So I only really, by heart, I only know that one by heart. After I know that one, I know the rest of them, because the rest of them you can derive. Right off the bat, I'm going to give you at least 4 more. Then you can sit there and try to memorize, or just watch. If I subtract cosine squared theta from both sides, then you can write the next one. And I'll tell you what, I'm going to make a list over here. If we start with sine squared theta plus cosine squared theta equals 1, the next one, sine squared theta is 1 minus cosine squared theta. So now you have a substitution that you could make for sine squared, or a substitution you could make for 1 minus cosine squared. You can turn it into sine squared. And of course, if you can do that, then you can do this. Subtract sine squared theta from both sides. And now you have cosine squared theta is 1 minus sine squared theta. Always. Well, what about tangent? Well, some of the other ones. I'll give you the answer and then we'll figure it out. I'll get there. Tangent squared theta plus 1 is equal to secant squared theta. This will make that. And how? You see tangent squared? To make tangent squared, tangent is made by sine divided by cosine. Sine over cosine. So all I need is sine in the numerator, cosine in the denominator. And then if I'm going to have, that means if I have cosine in the denominator, I want cosine squared in all the denominators. Because if you divide 1 by cosine squared, you got to divide everybody by cosine squared. If you divide 1, you divide it all. And that's where tangent squared comes from. Sine squared over cosine squared is now tangent squared theta. Cosine squared divided by cosine squared is plus 1. 1 over cosine. What is that? 1 over cosine. Oh, I erased it. Right. 1 over cosine, secant. So 1 over cosine squared is secant squared theta. That's for that one. And you don't have to write these down because you know you can manipulate it. Subtract 1 from both sides. Tangent squared is secant squared minus 1. Subtract tangent from both sides. 1 is equal to secant squared minus tangent squared. There's all sorts of manipulations you can make for substitutions. When you can't solve something the way it's written, you have this identity that allows you to change what you can't do into something you can do. So the other one would be, if you can make tangent squared, you can make cotangent squared. So if I want to make cotangent squared, it's going to look like this. 1 plus cotangent squared theta is equal to cosecant squared theta. And if you want cotangent, cotangent is cosine over sine. So I want cosine squared over sine squared, so everybody gets divided by sine squared. And if I divide everybody by sine squared, there's 1 plus cosine over sine is cotangent, so cosine squared over sine squared is cotangent squared theta. 1 over sine is cosecant, so 1 over sine squared is cosecant squared theta. So right there are 5 identities based on Big Daddy theorem. Sine squared plus cosine squared equals 1. And based on these identities. These identities set everything in motion. What else is it? If you can't do the way it's written, what can we simplify or change it to? Okay. You're going to solve equations that look like this. You cannot solve that problem because you have conflicting trig functions, sine squared and cosine. You're just not going to be able to work it out. You want all sines or you want all cosines. We really aren't going to be able to convert nicely a cosine to the first. If you want cosine to the first, you'd have to take the square root and you need pluses and minuses. But you know that sine squared can be rewritten as 1 minus cosine squared. So 1 minus cosine squared theta plus 3 cosine theta minus 2 equals 0. So that means negative cosine squared theta plus 3 cosine theta. 1 minus 2 is negative 1 equals 0. Now, I would never try to solve it with a negative, so everybody gets divided by negative 1. Because I would rather try to work positive cosine squared theta minus 3 cosine theta plus 1 equals 0. I don't know if it has a solution because I'm making that up on the top of my head. Right now, it's not factored. But guess what? The ones you're going to do in class, you're going to have to remember how to factor. Let each factor equal 0, and we're going to solve based on Mr. Units of. Okay. But the key was you cannot solve it because you've got two, arguing different kind of trig functions. Rewrite it with only one. Yeah. So that. Applications. Angles of elevation. When you feel elevated, you feel like you're happy, your elevation, the elevator takes you up. Now it doesn't bring you down, it only takes you up. An angle of elevation is when you, from the horizontal, it's always based on the horizontal. An angle of elevation is based on a horizontal parallel to the ground. the angle you make with the horizontal looking up. Yeah, looking up. Okay. Angle of depression is when you're above something, and again, horizontal line, but depression means you're looking down from that horizontal line of sight. So you look straight ahead, and then depression is the angle you measure when you look down. Angle of depression, like if you were standing over, on a cliff, and you're looking straight out over the cliff, and then you look down at a boat out on the sea. What's the angle of depression? We're standing on top of a building. You look down at a car. That's the angle of depression you're moving. If you're on the ground, you're looking up at the building. Angle of elevation. From the horizontal, looking up. Okay. When we do those examples, we'll do them right out of the homework. And we'll do those out of the homework. So we did out of the homework. We talked about that one. And I know, did we do any of the homework? I don't think so, did we? One to six, all. So one, it's just like, all right, which one is sine? Sine is opposite over hypotenuse. So that would be I, right here. I. Okay. You ever give your phone number to somebody using Roman numerals? Okay. I, D, D, I, D, DI, DI. That's the phone number I grew up with. Relative to the acute angle theta, the three sides of a right triangle are the acute angle. So the adjacent side, the opposite side, or sorry. There's only two that have the word side, one that doesn't. So the hypotenuse and the opposite side of the adjacent side. So because hypotenuse would not have hypotenuse side, we would never say that. Hypotenuse and then opposite and adjacent. An angle that measures from the horizontal up. Oh, angle of position. And looking down. Angle of my child. Depression. Man. You guys are my teeth therapy. Yeah, I'm good at therapy. Nobody's laughing at anything I say, so it's like, hey, it's out there, It's happening. Okay. And you guys, what is the length of the hypotenuse? If you can't figure out that that's 13, well, we got problems. Okay, so 1 through 6 are 7 to 35 off. Let's do number 9. Now let's do number 7, because I like number 7. The reason why I like number 7, number 9, you're supposed to find all 6 trig functions, all 6 trig ratios. Number 9, they give you both legs. So you don't have a hypotenuse, Pythagorean theorem. But on number 7, they start you off basically being tricky. You're not given the legs. You're given one leg and a hypotenuse. Usually people get number 7 wrong because they try to use 41 squared plus 9 squared. 41 is not a leg. 41 is the hypotenuse that you set it equal to. So this is what it would look like on a test of quiz. Because I know, and I don't take for granted that students will do what they're supposed to do. I always make sure in a problem like this. To list over here so you can put your answers. What's the sine of theta? What's the cosine of theta? what's the tangent of theta, and then right across, so you know exactly, you can just flip it over to get this. What's the cosecant of theta? What's the secant of theta? So they run together. And what's the cotangent of theta? Since you got to find all 6 anyway, why not practice your homework like I'm showing you right now? Okay? Because that's how I'll have you fill it out on the test and the quiz all the time. Those will be the blanks. Okay? Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Now I'm not going to do opposite over adjacent, hypotenuse over opposite, hypotenuse over adjacent, and then opposite over adjacent over opposite here. I'm just going to find these 3 answers, and then I'll flip these over. Opposite is 9. Hypotenuse is 41. Sine is ready to go. 9 over 41. So cosecant is ready to go. 41 over 9. But that's all I can do. For cosine, I need adjacent. And for tangent, I need opposite. And I need adjacent. So let's just call this. You can call it whatever you want. I usually will call horizontals, x's, verticals. I'll call those y's. Because eventually we're going to transplant these onto an XY axis. And if you don't set this up right, that's where you mess up. X squared plus 9 squared equals 41 squared. So x squared plus 81 is equal to 1600. 1600. Subtract 81. Well, look how nice this is. X squared is equal to 1600. Take the square root, and x is equal to the square root of 1600. You're going to get, do I put plus and minus 40? Am I going to need that? No. It's the length of a triangle. Length will only be positive. Now look how nice these numbers are. Integer, integer, integer. If you get nice integers for your triangle size, that's called a Pythagorean triple. Okay, a Pythagorean triple. There's lots of Pythagorean triples that are integers that make up right triangles. Mentioned this before. You know, the most basic of Pythagorean triples is the 3, 4, 5 right triangle. All right, pop quiz. 3, 4, or 5. Which one has to be the hypotenuse? The 5. Because the hypotenuse is the longest side in a right triangle. Okay. But if you take a look over here, what do we get? We got 40, top right. There it is, 9, 40, 41. It's on the list. If this was a quiz, you could have that list out if you made one. But look how long this list is. Oh, I like giving triangles that are 696, 697, 985. And again, these are the ones where the numbers don't reduce. They're not like I just multiplied 3, 4, 5 by 2 and get 6, 8, 10. You know, 6, 8, 10 is not on here. But if I multiply by 2, 6, 8, 10 works. Multiply by 3, that'll work. Multiply by 8. Okay. All I did was Google Pythagorean triples. And I didn't go to actually articles. I went to show me the images, show me pictures. But, you know, I don't do that. I don't do the pictures. And I just put this into a Word file. That's what I meant. And it's really nice to just, you have it at your disposal. And if you ever like question, oh, is it really a Pythagorean triple when you got one? You can always check. Now, (40 over 41), 41 over 40, opposite over adjacent, so 9 over 40 and 40 over 9. Okay. And same thing with 11. Find the exact value of the 6 trig functions of angle theta for each of the triangles. Explain why the function values are the same. So you're supposed to do it for that big triangle, and then you're supposed to do it for this little triangle. So Pythagorean triple. If the hypotenuse is 10 and that's an 8, well, that has to be 6. Has to. 100 squared minus 8 squared would be 36. Take the square root, that has to be 6. If you take 10 and divide by 5, you get 2.5. Oh, sorry, divide by 4. Take 10, divide by 4, you get 2.5. If you take 8 and divide by 4, you get 2. So this triangle here is just 1/4 of that triangle there. So if this is 6, this will be 2/3, or sorry, 3 over 2, 1.5. If you do the sine over, the 6 trig functions for this, it's going to be the same ratio. Sine will be 1.5 over 2.5. That's going to be the same as 6 over 10. Okay. The reason why they're the same is because this is just 1/4 of that triangle. The ratio of the sides are still the same. All the sides. That has to do with 2 triangles being similar. If 2 triangles are similar, then all 3 sides are in proportion. Therefore, the trig ratio is going to be trig ratio is going to be the same. So right here, 17. If I give you 1 trig ratio, you know all. So on 17, you're told that tangent is 3. The tangent of theta is 3. Sketch a right triangle. The visual helps, it really does. First of all, when they're telling you that tangent theta is a 3, don't forget to put that in as one of your answers. Maybe you can't figure anything else out, but if you don't put that in as one of the answers on a quiz or a test, why lose the points? And if you know tangent, what else do you know? You gotta know cotangent because you just gotta flip over the tangent. What's the reciprocal of 3? 1/3. If you know one, you know at least two. But if you know one, you know them all. So this is 3 over 1. Make a right triangle. So tangent theta is an opposite over adjacent. A 3 over a 1. If you want sine or cosine, you need the hypotenuse. But you know the ratio of opposite and adjacent. It's 3 to 1. So now you can figure out what the ratio would be for the hypotenuse. I like to just call this z, since I usually call this x and not y, I call this z. 1 squared plus 3 squared equals z squared. So 1 plus 9 equals z squared. 10 equals z squared. Take the square root, and z is the square root of 10. You always simplify. So if you could simplify your radical, do it. Okay. No decimals, exact value. So leave it as a square root 10. Put it in your picture. That's why you drew the picture. Square root 10. So I need to make a confession to those of you who took 103. We like you. We tell you that when you have a radical in the denominator, you have to rationalize the denominator, or else it's not simplified. Well, that's a lie. And the reason why it's a lie is because you need to learn how to rationalize the denominator so you can do other things later on. You need to learn the technique. For that class, yes, it has to be rational. For later on, right now, you're going to have so many radicals in the denominator, it's just going to be, you know what, you had the right answer, you're doing 5 other things. Why take your correct answer and in a hurry, you're going to get it wrong? Now, here's the dilemma. I don't need you to rationalize denominators when you turn stuff in on test or quizzes. You can if you want to. If it bugs you, what bugs them, they rationalize it. When you look in the back of the book, it's going to be rationalized. So you're going to think it has to be rational. I did the problem. I did what he told me. I look at the back and it's wrong. It's not wrong. It's just not rationalized, which is perfectly fine with me. Okay? Because when you get to this guy's textbook in calculus, he doesn't rationalize anymore. Okay? It's like a rite of passage. I don't know. Okay? Opposite 3 over square root 10. If you did rationalize, it would be 3 square root 10 over 10. That's what it would look like if you rationalize. Here's why I don't think you want to rationalize. The cosecant is the reciprocal. Flip this over. We get square root 10 over 3. Versus flipping this over. 10 over 3 square root 10. Are you now going to want to do the rationalization game? This is now just, it looks horrible. But now if you don't rationalize it, you have an ugly answer. I'd rather have you just turn this and this in. You got this right. Why run the risk of rationalizing and turning the correct answer into a wrong? That's why I grade work. Okay. Cosine would be the adjacent over the hypotenuse, so 1 over square root 10. And so flip it over, square root 10. Now, if you put square root 10 over 1, that's not simplified. Square root 10 divided by 1 is just square root 10. Right? You know 1, you know all 5. Sorry, you know all 6. So when you get to these guys, this is going to be important because this is where we're picking up with our most important angles, the 30, 60, 90s and the 45, 45, 90s. From the unit circle, that's going to be the bread and butter, because those are what you need to know by heart. You need to know sine 30 is always going to be 1/2, cosine 30 is always going to be square root of 2. Sine 45 is always going to be 1 over square root of 2. Cotangent 45 is always going to be a 1. If you know the first quadrant of those angles, you know everything for the rest of your life. When I gave the toast at my son's wedding, most everybody in the wedding was one of my students. So I started quizzing them during my toast if they still knew, what's the cosine of 240 degrees? Well, actually, I said, what's the cosine of 4 pi? Only one. Only one. But she worked for the JPL, Jet Propulsion Laboratories. So you better know. All right. The quiz is on this piece of paper. So all you gotta do is make sure you put your first and last name on it, because I might have 2 Billies. You just put Billy, which Billy are you? The first and last name, show your work, okay? Make sure you put your right answer at the bottom when there's a space provided. When you're done, turn it in, you're free to go. Open notes, anything you want to have out, real calculator, no internet devices. There we go. This is also how I take roll. Blank paper. You don't want to go blank one. And this is the days when you didn't wear a mask, so you could lift your finger to get the pieces of paper apart. Or at the store, you could get the damn plastic bag. Come on.